you worked to develop AT1, one of the time scales. That's still in operation or used today?
Yeah, Jim helped me, and he had written an algorithm based on his thesis for timescale. And when I had the responsibility for the clock system, he was then section chief. And then I started working with some of these statistical concepts of how to take the time readings between an ensemble of clocks and how to combine them optimally. And I came up with an algorithm that weights the clocks, both short-term and long-term, due to their segmental performance. So you have a weighting scheme which can be dynamic, namely you learn the clock's performance, and as the clock changes, you kind of breathe and go with what the clock does over time. And so you have an optimum weighting for each of the clock in the ensemble. You can show that when you do this, you end up with ensemble time which is better than the best clock. And even the worst clock enhances the output. So it's a beautiful concept. It also is robust. It can deal with malfunction. And I remember one time I ran the scale and I had 8 clocks and 3 of them failed on one measurement cycle. And it picked up all 3 errors and walked on through. And so anyway, you have this robustness and elegance and the fact that it can be real time. US&O would calculate their time from like 60 atomic clocks. We had 8, and we could show that our timescale stability with a good environment was better than theirs after the fact. So the fact that you had both a real time scale and a breathing system, and it would deal with white noise and flicker noise, made AT1 extremely useful. And as far as I know, they're with lots of upgrades by G. Levine and several others with dealing with drift of hydrogen masers is still being used today.
And so what's at the heart of it? Is it it's a software? I mean, it takes measurements that have been performed with hardware, like with this dual mixer time difference technique, and then it uses software to compute the weighting, the proper weighting, and then put an output. And what is this? So what is the format of the software? What language is it written in?
Well, back when we got our first timescale computer, it was a PDP-8S, a big tall thing with 8 kilobytes of memory. And 92 lines of code.
How long is each line? That seems pretty compact code.
It was Fortran 4. It was really a fun program. And so you would make a set of time difference measurements between all of the clocks, and you would then compute the time error. You determine optimum time, and then you look at the time error of each. And the time error of each then would update through a recursive filter, an exponential filter, the weighting factor. So every time you'd take a measurement, you'd get an update. And so every time you made a measurement, you'd also compute time as well as update the weighting factors. So it was a breathing scale, always dynamic and changing appropriate to the clock's behavior.
And is there a physical output, like you steer a chord,
yes,
a single chord's based on
thanks
everything?
Thanks again to Judah. We had a rubidium. I think it was the first thing we tied to the software clock. So we had a real-time output that would be tightly synchronized to the software clock. So that then became your output signal, chasing servoed to the software value that was computed by the ensemble. And then that ensemble, of course, is calibrated against your primary standard so that you know that the rate is correct with respect to the primary seasoning frequency standard.
And it's also used in international comparisons, right, via satellite. So how does NIST tie the output of this time scale into international time?
So back in
Or NBS.
Yeah, we the V11 and WWV. I mean, that goes way back, and then later on you had Loran-C, which was a navigation system that the Department of Transportation operated with cesium clocks, and those were synchronized by the Naval Observatory so that ships at sea and airplanes could do Loran navigation. So you had cesium clocks at these transmitters. And those clocks were distributed so that we could listen to a Loran station in Boulder, and it could be, we could go chain across the Pacific all the way so that people at the Paris Observatory, where the International Bureau of the Hour was, where time was kept back then, Bernard Guinaud was in charge. So we would transfer the times of our clocks from different world community clocks using Loran to go as a transfer system. And it was, we could see instabilities of the order of 1 or 2 microseconds over the course of a year. And it was really hard because the clocks were so much better than the propagation that it was
frustrating.
Really, it was frustrating.
Yeah.
Yeah.